Okay, we continue our program this afternoon with a really exciting topic where the moon has certainly figured prominently. We're going to see it from a different perspective and what kind of research is going on there, presented to us by Professor John Pober from Brown University. And thank you so much for taking your time in a lousy day to join us. And so let's please give John a warm skyscraper welcome.
Well, thank you. I really appreciate the invitation, and I'm really happy to share some of this with you. But before I start, I want to tell a little story because I caught the very end of that last talk. And so I want to say I was a physics major as an undergraduate until I spent a summer where I had spent 2 weeks on Mount Wilson and spent a night, dusk till dawn, with an eyepiece on the 60-inch. And that's when I added an astronomy major to my degree. I was totally overwhelmed by that. And so it was really nice to see that up there. But today, I want to convince you that there is a future in fundamental physics, cosmology, and astrophysics from the far side of the moon by putting a radio telescope on the far side of the moon. It's an incredibly ambitious experiment. And so for the first half of this talk, I'm going to really focus on the science that is driving this, right? If you can't have unparalleled science, you're not going to do this. This is such a daunting construction project, right? For scale, this square here is the footprint of the experiment we're eventually hoping to build. This is really ambitious, to say the least. And so for the first half of this talk, I want to tell you kind of where we are with our modern understanding of cosmology and what the limitations are, what we still want to know and what we can't know without fundamentally new information. And following that, I want to show you kind of the path we're on, building experiments, both here on the ground, but getting to this scale of an experiment on the far side of the moon. So what do we know about cosmology, and what are the limitations of what we know? That's really the thing I want to convey to you for kind of the first 20 minutes here, motivate the really hard part that I'll describe in the second part of the talk. And so whenever an astrophysicist thinks of cosmology, this is the picture that comes to mind. This timeline of the universe that basically describes how we think everything unfolded. From a big bang, all the way here on the left, 13.8 billion years ago, followed by rapid expansion of the universe's size during this period we call inflation. 400,000 years after the Big Bang, this afterglow light pattern labeled here. This is one of the most important events in cosmic history and one of the most important pieces of cosmological information we have. This is the cosmic microwave background. And what it is when the universe first went through this inflationary period, afterwards it was incredibly hot. So the Big Bang is often called the hot Big Bang. And our model is that as the universe expands, it cools down. And so in the early universe, the universe was so hot that ordinary matter couldn't exist. And only after it cooled sufficiently did atoms start forming. And neutral atoms of elements like hydrogen and helium were some of the first things to form. And this moment when the universe is finally cool enough to have neutral hydrogen is the moment the universe becomes transparent. Before that, it's a hot plasma. And plasmas of hydrogen are opaque. But as soon as neutral hydrogen forms, we have a transparent universe, and all the light from the Big Bang that was trapped in this primordial plasma is free to travel through the universe because it's now transparent. And we can observe that light today in the microwave. It's the cosmic microwave background, and that light is a snapshot of what the universe was like 400,000 years after the Big Bang. And so I want to focus a lot on the cosmic microwave background. It is one of our most important pieces of cosmological information. But it's early in cosmic history, 400,000 years. Following that, there's this period, the Dark Ages, when the universe is very simple. It's hydrogen and it's helium. No stars, no galaxies, just gas. And it's the evolution of the universe through the Dark Ages. So when we look at the cosmic microwave background, we see these very, very small fluctuations that are small over-densities in the average density of the universe. It's regions that are a little bit more matter. than elsewhere in the universe. Given 400 million years, gravity wins. So the places that have a little bit more matter have a little bit stronger gravitational pull, and they start pulling more matter in and more matter in. And eventually, you get clumps that are dense enough to form stars and form galaxies. And so we go through this moment of cosmic dawn, the first light in the universe after the Dark Ages. And as the universe continues to evolve, stars assemble into galaxies, galaxies assemble into larger structures, and we get our modern universe. And just to complicate things, we have this period at the end, dark energy accelerated expansion. We would have expected the universe to slow down in its acceleration as gravity starts pulling things back together. But 25 years ago, it was discovered that the expansion of the universe has actually started to speed up in recent times, cosmologically speaking, at least. And was completely unexpected. And so this is our timeline of the universe in a nutshell. We go from the Big Bang through inflation, form the cosmic microwave background, and evolve stars and galaxies over billions of years. But there's a lot that we don't know about this picture. Fundamental questions about the early universe. Is this inflationary period, this rapid expansion, really part of our cosmic history? It provides a very nice explanation for why the cosmic microwave background looks the way it does, but it's not the only explanation. And so we don't know what was the Big Bang, what happened at the very beginning of the universe. This middle period is also quite complicated. We have gas forming stars. Stars explode in supernova. Supernova feed back on the gas that formed them. This growth of structure is a very complicated process. Dark matter forms a very important backbone of galaxies. But how does dark matter and ordinary matter work together? And eventually, once you get that first light, once cosmic dawn happens and light starts permeating the universe, how does that change the universe? Are the next generation of stars and galaxies different? These are questions. And as I already alluded to, this late period of accelerated cosmic expansion is a complete mystery. What is dark energy? Is it a breakdown of Einstein's general relativity? Is it something simpler? We don't know. And even with all of these questions that I'm going to say this 21 centimeter cosmology experiment that I'm going to describe to you can answer, we of course always have to ask, what's missing from this picture? What's unexpected out there? So much of cosmic history is unobserved and only described by theory. What are we actually going to find when we observe it? So I said I want to spend a fair amount of time talking about the cosmic microwave background because it's the most important piece of information about our cosmic history that we have, but it's the limitations of the cosmic microwave background that drive us to do this next experiment on the far side of the moon. And so, as I already said, the CMB probes the universe 400,000 years after the Big Bang. Some places you'll see 380,000, depending on how accurate you want to be. But this image of the cosmic microwave background from the Planck satellite, these are small fluctuations in the density of the universe that seed all the structure to come through this process of gravitational collapse. Little denser regions, as I said, pull in more stuff over time. One thing that I don't know is often stressed enough is how small these fluctuations in the cosmic microwave background are. So if you imagine this map is the surface of a sphere, it would be smoother than a billiard ball. These fluctuations that we highlight in these images are about 1 part in 10 to the 5. So the universe is extremely smooth in its early history. It's only with, again, millions and billions of years of evolution that those small little bits with extra matter can continue to grow and seed stars and galaxies. So it's an amazing picture, but how do we get science out of the cosmic microwave background? What does it tell us about the universe? And so all these little spots, all these fluctuations, they're not completely random. So no theory will tell you the location of a hot or cold spot in the cosmic microwave background, we would say. So I cannot write down a cosmological theory that says Look here, and you'll see a hot spot. Look here, and you'll see a cold spot. Look here, there'll be another cold spot. That's not a prediction. But the statistics of these fluctuations are predictions of theories. And so we need to analyze this map statistically to understand what it tells us about the universe. The statistic we're going to use is what's called the power spectrum. And so what the power spectrum is a map of how strong those fluctuations are at different angular scales, right? So the bottom is angular scale. And you'll notice this power spectrum peaks at about 1 degree. And that's something you can see looking at these maps. These dots have a characteristic size to them. There's a lot of dots that are the same size, and they're about 1 degree big. And so that's what the power spectrum tells you. There are more 1 degree fluctuations than anything else. But there's also other preferred scales. Here at 1/2 degree, here at 1/4 degree. There's all this structure that says those fluctuations are not just random noise. They have structure to them. And it is that structure that we can predict from theories of the universe. So a prediction from theories like inflation and other explanations for the Big Bang are what this power spectrum will look like. So the red points, those are the data from the Planck satellite. That it took that image of the CMB, performed this statistical calculation on it, and came up with those red points. The green line is a fit based on the cosmological theory of inflation, again, this rapid expansion in early cosmic history, and how the universe then evolves towards the CMB. It's a fit with just 6 free parameters in it. And those free parameters are things like how much ordinary matter is there in the universe, how much dark matter, how much dark energy, curvature of the universe, whether the universe in general relativity has an overall curvature to it. We figure out the values of those numbers by analyzing this data and performing this fit on it. And it's tremendous, right? The accuracy with which this green line agrees with this data. The CMB is an incredible success, and it's why cosmology went from being a pencil and paper science to a precision science, that we can actually constrain these values to percent level. But there's some fundamental limitations as to what we can do with the cosmic microwave background. One of them is our ability to measure what's going on the largest scales of the universe. So you may notice this green line here has this big shaded region around it, all the way on the left, where these really big angular scales, 90 degrees, 45 degrees. And that's a fundamental statistical limitation. Right? Take the entire sky. How many 45-degree patches do you have to measure? Not that many. Right? 45 degrees is a big chunk of the sky. And so you're just limited by the number of fluctuations of these very, very large scales that you can possibly measure. We call it cosmic variance. We have one universe. It has one set of fluctuations associated with it. And we can't get the statistics on the very, very large scale fluctuations measured very well. We'd love to. If you look at this data, some of the red points out here don't agree with the theory fit. This 90-degree one is just barely on the edge. Down here at 10-ish degrees, you can see that point falls off the theory curve. How significant is that? Well, you can do statistical calculations, and you find it's about a 1% chance that just by chance, you get that point to be that low. Now, in your everyday life, if you have a 1% chance, that's not a very good chance. But for cosmology at the percent level uncertainty, we'd like to know better than that, right? Because the explanations for why these points disagree are absolutely fantastic. Things like multiverses, where another universe has collided with our universe and changed the overall shape of the sky, right? Fantastic descriptions that if there were observational evidence for a multiverse, that would be incredibly exciting. But we don't give out Nobel Prizes for 1% chances. And so we need better statistics. But we can't get them from the cosmic microwave background. As I said, we've measured all those large scale modes. We've measured the 45-degree patches. We can't measure them any better, and we can't get any more of them. And so there's really a limitation here to what we can do. There's also a limitation on the other end of this plot, at these really small angular scales. At least for a cosmologist, these are small scales. Think about 5 arc minutes is where the resolution of the Planck satellite is falling off. But it's not just the resolution of the experiments. You can see the signals over here are bright. They're big numbers. The signals over here are down near 0. And that's actually a feature of the cosmic microwave background. So here's another plot. It's on the same scale. Now the angular scale's up here on the top axis. This bottom axis, multipole moment L, it's a cosmologist counting number, but think angular scale. Right? Whereas Planck was done around 0.07 degrees, the Atacama Cosmology Telescope and the South Pole Telescope are ground-based telescopes with better resolution. They've measured this down to 0.04 degrees. But you can see the power, the brightness of these fluctuations is just dropping, dropping, dropping. There's not signal out there to measure. Even if you build a telescope with arc-second resolution, the signal's not there. And that's a fundamental feature of the cosmic microwave background. As I said, the CMB is the light from the Big Bang traveling through the universe once the universe becomes transparent. It is photons. And if you try and take a big chunk of photons and squeeze them all together into a really, really small scale, radiation pressure pushes them back apart. Photons don't clump. They don't cluster in the same way as ordinary matter because it's light. It likes to travel outward. And so this suppression, the lack of power at these really, really small angular scales is an inherent feature of the CMB. But if we can understand what the universe itself was doing on those very small scales, there's tremendous information. The nature of dark matter, the masses of the neutrino, which is a major problem in modern physics, the possible curvature of the entire universe, better measurements at those small angular scales as to what the universe looks like would help us answer those questions. But again, it's a fundamental limitation of the cosmic microwave background. You can't get those measurements. There's no power there. There's no signal there. So I'd be remiss if I didn't point out another major technique we have for probing cosmology. And that's instead of looking at the cosmic microwave background, to map out the distribution of galaxies on cosmic scales. And so what you see here is a map from the Sloan Digital Sky Survey. We're here at the center of this image, looking back in cosmic history. So all the way out here, 13.8 billion years ago, that's where the cosmic microwave background is. But every single one of these dots is the location of a galaxy. And so you can measure the statistics of those galaxies and use them much in the same way as you use the cosmic microwave background. But you see there's a lot missing here, right? The most distant of these galaxies go back maybe 2 billion years. The universe is 14 billion years old. And so all of this black space is fundamentally unobserved by this technique. There's a tremendous amount of the universe we haven't seen. But galaxies have a further problem, these galaxy surveys, which is that making galaxies is extremely complicated. If we want to know what the universe is doing on really, really small scales, well, galaxies have their own physics going on really, really small scales. Star formation, supernova, shocks. Making galaxies is hard. And so if you observe something unexpected on small scales in a galaxy survey, you have to ask yourself, am I seeing something weird because the universe is fundamentally different than I expected? Or because galaxy formation physics is really complicated and I don't understand it that well? Odds are it's the latter. And so we need a way to probe the small scales of the universe without this added complication of astrophysics. So here's one more timeline of the universe. Same general picture as that first one we saw, but a different scheme. And with this timeline, why I like it, it highlights those dark ages, that period of time between when the cosmic microwave background formed and when the first stars formed. When I said the universe was very, very simple. And that period of cosmic history, if we can observe it, it will solve those problems I mentioned. Instead of being a surface of the sea, like the CMB, where we just look at one plane of the sky, it's a volume. There's a history there. And it's very, very simple physics. The universe is hydrogen, helium, dark matter, gravity. We can model what's going on in the dark ages. And so if we see something that doesn't look like our expectation, it's not because of messy galaxy physics, it's because the universe is telling us something.
What was dark energy?
So dark energy, in our simplest understanding, isn't important then. Dark energy has only become important about the last 6 billion years. If we see evidence for something like dark energy happening in the dark ages, that's an important piece of information as to the nature of it. And so, again, we think we understand the physics very, very well. What that means is when we see something that doesn't match our expectation, it's worth following up on and understanding. But there's one fundamental catch. The dark ages are dark. There are no stars. There are no galaxies. There's nothing to look at, with one exception. And so that's what I want to tell you about. And so this is where my field of research, that goes by the name of 21 centimeter cosmology, comes in. And so let me explain this name to you. 21 centimeter refers to a spectral line of the hydrogen atom. So the hydrogen atom is a very, very simple atom. It's a proton and an electron. Hydrogen is everywhere. The dark ages are filled with hydrogen. And so if we can see the spectral line, we can see the hydrogen. What causes this line is a very, very low energy transition. So quantum mechanically, particles have an inherent angular momentum. We call it spin. Particles have spin. And there's a very small energy difference between the proton and the electron having their spins aligned and their spins anti-aligned. And that energy difference, if you know electron volts, it's about 1/1,000,000th of an electron volt. If you think in terms of frequency, the photon that comes out when it goes through this transition is a 1420 megahertz photon, or 21 centimeter wavelength. So it's a radio signature, but it comes from neutral hydrogen. And if you have neutral hydrogen, you can see the 21 centimeter line. And so if we go back to this picture, what makes 21 centimeter cosmology such an exciting prospect is, well, if we see hydrogen nearby emitting in this line, it's 21 centimeters. But if there's some hydrogen back here, when the universe was, say, half its current size, and that hydrogen sends out a 21 centimeter wavelength photon, well, the wavelength of that photon expands along with the universe. So if the universe was 1/2 its size when it got emitted, when it reaches our telescope, it's a 42 centimeter photon. And so by observing 21 centimeter and longer wavelength, we can map back and back and back and back in cosmic history. The longer the wavelength you see this line coming from, the smaller the universe was when it was emitted. And so if we build a radio telescope with a very big bandwidth and good spectral resolution, then we don't just get a map of the hydrogen on the sky, we can reconstruct this entire volume of the universe and what hydrogen was doing at all these different times in cosmic history, just by measuring different wavelengths. So this is a technical plot. I'll explain why it's interesting in a minute, but I want to go over again why these dark ages observations with the 21 centimeter line solve those problems with the cosmic ray background. As I said, the dark ages is a volume. And because we can map the wavelength of the 21 centimeter photon that we observe it at longer wavelengths, we can map that back to when in cosmic history it was emitted, we can probe that entire volume. And so we're not limited by the number of 45-degree patches on the sky, because we can measure those patches at the beginning of the Dark Ages, the middle of the Dark Ages, end of the Dark Ages, and all the periods in between, and get much, much better statistics. We don't have that small scale problem. I said the lack of small scale power in the cosmic microwave background came from the fact that it was made of light, and light doesn't clump. This is hydrogen. It's emitting light, but it's the hydrogen we're studying. Hydrogen clumps just fine. And so with the hydrogen signal, you can probe those very, very small scales. And so what this plot shows, and this L, this was the cosmologist's way of talking about small angular scales. Remember, the information in the cosmic microwave background from the Planck satellite went out to something like L of 4,000. That's something like here. And what each of these different lines are is a different model of exotic physics. Different models of inflation, different models of neutrinos, different models of dark matter. And if you can only model them out to L of 4,000, again, about 5 arc minutes, you can't tell them apart. But if you can get out to L of 100,000, much, much smaller angular scales, these all start looking different. And so we can start seeing different models for dark matter, different models for neutrinos, different models for the Big Bang. They start looking different, whereas they don't in the CMB. And as I've already mentioned, there's no complicated astrophysics during the Dark Ages. It's simple hydrogen gas, helium gas, dark matter with its gravitational attraction, but none of this messy gastrophysics, as people like to say, of galaxies forming and gas colliding and stars exploding. None of that's going on. So there's no complications in interpreting the signal. And so all told, if we can measure the 21 centimeter hydrogen signal from the Dark Ages, there's about 1 million times more pieces of information than we can ever hope to extract from the cosmic microwave background. We can just get those statistics so much better and start understanding some of these really interesting questions about the nature of the universe. It's hard to do these observations. There's a lot of challenges in going after that Dark Ages signal. So this is a plot of atmospheric opacity versus wavelength. So you may know the shortest wavelengths we have to do from space. Gamma ray astronomy is in space. X-ray astronomy is in space. That's because the Earth's atmosphere doesn't let those short wavelength photons through. That's a good thing. Being bombarded by gamma rays from space all the time is not good for living things. So our atmosphere is doing us a favor, but we can't do gamma ray astronomy from the ground. In the optical, there's a nice window here. Visible light makes it through the atmosphere. In the infrared, it's a bit of a complicated picture. There are windows you can see, but then there's water vapor that clouds out other windows. At longer infrared wavelengths, here, the atmosphere is totally opaque again. And so infrared satellites like the Spitzer Space Telescope shown here are in space. But radio astronomy is usually thought as a ground-based astronomy. You can see this atmospheric opacity window has gone all the way down to 0. Radio waves make it through the atmosphere. Until you get to about 10 or 20 meters in wavelength. And then the atmosphere becomes totally opaque again. That's due to the upper layers of the atmosphere called the ionosphere. And the ionosphere blocks out long wavelength radio waves. That's why AM radio can travel so far, is it bounces off the ionosphere and comes back down at a different location on Earth. But if you have a long wavelength radio wave coming from space, we can't see it. And that's exactly the regime a 21 centimeter Dark Ages experiment would be in. 10, 20, 30 meter wavelengths. We can't do it from the ground. It's blocked by the ionosphere. And so it has to be in space. In this frequency range, people are also a big problem. We make lots of radio waves. FM, AM, digital TV, satellite broadcasts, cell phones, crowds out the radio spectrum. And down at these very long wavelengths, it's not fun doing radio astronomy from the ground. I'll show you some ground-based experiments, but they're in very remote locations to get away from people and their radio emissions. And so that's another obstacle to these experiments. But given this atmospheric opacity problem, we are building experiments on the ground right now. We're in this regime where we can actually see through the atmosphere, but it also means we're not seeing light from the dark ages. Light from the dark ages, as I said, it's the wavelength stretches and stretches and stretches until it's here. What we can observe in the 21 centimeter line from the ground are from this cosmic dawn era. It often goes by the name of the epoch of reionization. The first stars are forming, the first galaxies are forming. And so let me show you what I mean by the epoch of reionization. So this is a simulation. The black that you see right now is neutral hydrogen. So the end of the dark ages, the universe consists of neutral hydrogen. Oops, get that play button back. But as the first stars form, the first galaxies form, they start putting out light. And they start putting out ultraviolet light that has enough energy to ionize the neutral hydrogen, strip the electron away from the proton. And so what you see here, these bubbles that are growing in this black hydrogen are bubbles of ionized hydrogen growing around the first galaxies. And eventually we have enough galaxies that these bubbles permeate the entire universe, a percolation process, where the entire universe becomes ionized by the first galaxies. And so by the time this process is over, there is no more neutral hydrogen between the galaxies. It's only in the galaxies that we find it. And so if we can observe the hydrogen at this time, we're not probing fundamental physics. We're not probing dark matter, dark energy, but we're probing the first galaxies and the first stars. And there's a lot of interesting questions about them as well. How were they different from modern galaxies? What were their masses? What were their clustering signatures? And all of that's encoded in the 21 centimeter signal. And so if we can measure these epoch of reionization because the hydrogen gas is again becoming ionized after it was that way in the early universe, we can learn a lot about the first galaxies. And so that's what we're trying to do from the ground right now. Unfortunately, I'm not done with the challenges inherent to these experiments just yet. The biggest one, other than the atmosphere, is all the other astrophysical radio sources out there. So this is a map of the radio sky from the northern hemisphere at 30 megahertz. We put it in coordinates of the plane of the Milky Way is running across the sky. The Milky Way is incredibly bright at low radio frequencies. You can see at the plane of the galaxy, also a lot of supernova remnants. They're very strong. So Cassiopeia A is the most recent supernova to have gone off in the Milky Way. It was the brightest radio source in the sky until 50 or so years ago. It's been fading on human timescales. This feature up here, the North Polar Spur, is thought to be a very nearby supernova remnant. It's the shell of that supernova remnant. But the sky is just filled with radio emissions. And altogether, it's something like 4 to 5 orders of magnitude brighter than the 21 centimeter signal. If we're talking about the dark ages 21 centimeter signal, that signal is even fainter, and these radio sources are even brighter, something like 8 or 9 orders of magnitude stronger. So we're looking for a needle in a haystack, where we have to pick out the signal we're looking for from all this bright emission. We think we can do it because they have different spectra. We take the spectra of the signals, the radio foregrounds, we call them, because it's all the radio emission between us and the hydrogen signal way off at cosmological distances. The foregrounds look different in their spectrum from the 21 centimeter signal. So we believe they can be separated, but it's very challenging. Still not done with the difficulties. This is a hard experiment. The signal is very, very faint. You want to observe a faint signal, you need a big telescope. Some numbers to keep in mind if you want to observe that epoch of reionization signal. We need about 1/10 of a square kilometer of metal. So not 1/10 of a square kilometer, we spread out our antennas across that area. That area needs to be filled with metal, observing for about a year. To do the dark ages, as I said, that signal is much fainter, we need about 5 square kilometers of metal running for about 5 years. So it's a big experiment that needs a lot of investment. I've already mentioned these local challenges, radio frequency interference that we generate with our electronics, and the ionosphere. It's opaque at the longest wavelengths, but at the wavelengths we can observe from the ground, it does what seeing is for optical astronomy. It's a time variable turbulent plasma up in the atmosphere. It refracts radio waves, makes our sources dance around on the sky, makes everything harder. I'm sure you all know. Seeing is, when it's not good, it's not good. And fundamentally, the response of a radio telescope, we like to say, it's chromatic. It changes as a function of frequency. And a radio telescope is a piece of metal out there to respond to radio waves. And that metal is going to interact a little bit differently with radio waves of 1 meter versus 1.1 meter versus 1.2 meter. And that little difference, it's little, but we're trying to tell our signal, our needle in a haystack, apart from the haystack, the foregrounds, based purely on their spectral properties. And so if we don't correct for the spectral response of our telescope, we can't separate the two. And it's very, very hard. So if you were to ask me what I spend most of my days doing, it's figuring out how to measure the spectral response of my radio telescope to 1 part in 10 to the 5 as a function of time and antenna. That's what I spend most of my time doing. That's one of our biggest challenges. But we are doing this. So the last little bit here, let me tell you about the experiments that we have built, that we will be building, and that we want to build to make this a reality. Hopefully I've convinced you that the science is exciting enough that this is a path worth pursuing, and there just isn't any other way to go after that science. So on the ground, we kind of have a first generation of experiments that have completed. So this one in the upper left, the precision array for probing the epoch of reionization. I apologize to anyone trying to Google that telescope. You can't find it. Paper telescope is not a very helpful search term, but that was my PhD thesis. I was in South Africa for about 8 hours from Cape Town in the Karoo Desert, and we just need to be away from people. The Murchison Wide Field Array, for each of these little smudges you see in this image, are antennas. I'll show you a close-up of those antennas. It's in Western Australia, again, about 8 hours from Perth, another very radio quiet region. There's LOFAR, the low frequency array, that's in the Netherlands. And GMRT, the giant meter wave radio telescope, that's in India. All of these experiments started operating around 2008, 2010, took years of data, and taught us a lot about how hard this experiment is. We've since moved on to a second generation, so LOFAR, still operational. The Murchison Wide Field Array has undergone several upgrades. And so you can see these antennas a little bit closer. Each of those little spiders is something about this big. There's 256 of those tiles of antennas out there in Western Australia. And then the newest experiment, the Hydrogen Epoch of Reionization Array, that's in South Africa, the same place Paper was. The scale is hard to tell. Each of these dishes is 14 meters, and there's 350 of them. So hair is very, very large. There's also a suite of experiments going after even higher frequency radio signals. So the 42 centimeter regime, where instead of probing the first galaxies, we're mapping out modern galaxies. As I told you, surveying the positions of galaxies is a powerful cosmological technique. And so surveying the position of galaxies, there's Tianlai in China, SHINE, the Canadian Hydrogen Intensity Mapping Experiment in Canada, which the name suggests, and HIRAX is a concept for a new array also in South Africa. Tianlai and SHINE were built, they've operated for years. It's outside the scope of the science I'm talking about right now, but fast radio bursts are a new phenomenon, about 15 years old now. The name tells you about as much as we know about them. The bright flashes of radio waves from seemingly extragalactic sources. It used to be a joke that there were more theories for what an FRB was than observed FRBs. Chime in particular has changed that. It's seen hundreds of these things. And so it's really created a brand new field of studying what fast radio bursts are. And we want to build more telescopes on the ground. So Hera may not complete construction. Funding may have fallen a bit short. But the MWA has undergone its phase 3 upgrade at the beginning of this year. We revamped the entire digital electronic system. And I'm personally very proud of the telescope. Brown University just took over as the lead US organization in the project. But I think it's that upgrade to phase 3 makes it a fantastic piece of equipment. And I'm excited for science to come out of the MWA. Both those telescopes, MWA and Hera, are precursors for what's called the Square Kilometer Array, or SKA. Here's a rendering of what the SKA might look like. So those dishes in the background are a different telescope. The SKA would be something like this farm of what we call Christmas tree antennas. There's 256 of them in this cluster here, and there'll be something like 500 of these clusters spread out across Western Australia. So a very large telescope, right? 1 square kilometer of metal. But what about that dark ages signal I talked about? If we can't do that from the ground, how are we going to go after that and get the cosmology that's really driving all of this? We need to go to the far side of the moon. Why the far side of the moon? Well, the lunar surface is the only place we can put 5 square kilometers of metal for 5 years. That was the number I said we needed roughly to make a detection of this signal. It's just too big to have floating in space. The moon has little to no ionosphere. So the ionosphere, the upper layers of the Earth's atmosphere, were opaque to the signal we were after. We need to be up in space. Well, the moon has effectively no ionosphere. You can see those radio waves. The far side shields us from terrestrial interference. All the radio emission coming from Earth is blocked by the moon itself. And so the far side of the moon is the radio quietest place in the inner solar system. And it really is the only place this experiment can be done. So how are we going to get there? There's a lot of challenges, engineering challenges, science challenges, to actually building this array. How do you get 5 square kilometers of metal on the far side of the moon? There's a number of different proposed approaches. We'll talk about some of these experiments in more detail in a minute, but there's proposals where we have rovers drive out tethers, and inside the tether, radio antennas are embedded. Getting the data back from the far side of the moon is a big challenge. You can't send a radio signal from the Earth to the far side of the moon. That's the entire reason we're there. And so we need something like an orbiting satellite collecting our data when it's overhead, beaming our data back to the Earth when it's on the near side, but actually getting the data through that link. These telescopes create much too much data to do that without a significant engineering work on the ground to process some of the data in real time. And so what I like to say is with these experiments, the real challenge in designing them is a balance between deployability, the actual feasibility of putting 5 square kilometers of metal on the far side of the moon, and calibratability, building an experiment that we can model with enough accuracy to actually overcome all the other challenges that I described. Right? This antenna does not look like the MWA antenna, but putting 100,000 dipoles of about this size that currently are built by teams of graduate students on the far side of the moon, I'm not sending my graduate students anytime soon. So how are we going to get an experiment that looks like the MWA up there? We aren't. So we have to balance these competing tasks. But radio telescopes are going on the moon very soon. In 2023, ROLS's, which is a mouthful, the radio wave observations at the lunar surface of the photon electron sheet, that's even more of a mouthful, But this experiment, this is part of NASA's commercial lunar payload services, so where they're contracting out to private companies. A company called Intuitive Machines is going to land this experiment on the near side of the moon next year. And it's going to study what we call the photoelectron sheet. The moon has no atmosphere, and so high energy photons from the sun are hitting the surface of the moon, they're charging it, they create a little bit of an electric field on the surface. We need to know how that looks in detail to model how it's going to interact with radio telescopes, and ROLS is going to help measure that. But in 2024 and then 2025, two parts of an experiment called LUCY, the Lunar Surface Electromagnetics experiment, are going up. LUCY Light will be near the south pole of the moon, in the Schrodinger Basin. It's going to measure surface plasma physics, magnetic fields, a lot like ROLS's, but with even more accuracy. But then in 2025, what we're calling LUCY Night is going to go to the far side of the moon and be the first real pathfinder for a 21 centimeter cosmology experiment on the far side. 2025 is not that far away. But again, this is a far cry from 5 square kilometers of metal. So I don't want to claim we're building that experiment in the next couple of years either. But looking a little bit further into the future, an array concept we call far side, where we have a lander, currently courtesy of Blue Origin, deploying these 4 single axle rovers, and each of these rovers will drive out this tether, which will span about 10 square kilometers in this star pattern. So there'll be 32 antennas embedded in each tether, 128 total antennas. It's still too small to do 21 centimeter dark ages cosmology, but there's a lot that can be done studying exoplanet magnetospheres, space weather, basically looking for the aurora around exoplanets. And it's particularly interesting because most of the extrasolar planets we know are around M dwarfs. We know M dwarfs have very different weather than the sun. And so even if you see an extrasolar planet the right distance from an M dwarf to have liquid water, we need to know how active coronal mass ejections and other space weather phenomenon are from those stars, and whether the planets have magnetic fields to protect them like the Earth does. So this is potentially the first way to measure magnetic fields of extrasolar planets and see if they have protection from solar winds. Bigger still, we're moving into the concept regime now as opposed to the mission regime. There's the Lunar Crater Radio Telescope, or LCRT. The idea is to use a crater on the moon to build something like Arecibo, the telescope in Puerto Rico that collapsed a few years ago now, or FAST, which is a radio telescope in China, but they're using kind of a natural karst system to help build a dish. Here we're using a lunar crater to support a 1 kilometer diameter dish. So with the lower gravity, you can build a much, much bigger dish than you can on Earth.
No.
It also helps that chicken wire, effectively mesh, is a mirror at these long radio wavelengths. So we don't need solid paneling. You can build this out of a wire mesh and it will be completely reflective to radio waves. And then kind of our ultimate vision for a telescope that actually has the collecting area to do the dark ages science, we're calling far view. And far view, the idea is that it's so much metal we need on the moon, we're not going to land it there. We're going to manufacture it out of the lunar regolith itself. And so have rovers that collect lunar regolith, bring it back to a processing unit, and then have an antenna that basically we can deposit on the surface of the moon and connect up to a central processor to get that 5 square kilometers of collecting area that we need. That is the word, ambitious. So again, this is a roadmap from ROLS's next year to far view is 1 to 2 to 3 decades of development. But it's development that is happening now. And so hopefully I've convinced you that as ambitious as that sounds, the science that we can do is completely unique. There's no other way to do it. And it can really answer some of the remaining mysteries about the nature of our universe. The experiment is incredibly demanding. We're learning a lot from building experiments on the ground. We're starting to get dedicated research and development funds for lunar experiments. And within the next 10 years, I expect there will be smaller lunar arrays like that Farside experiment, studying space weather, but serving as a pathfinder for even bigger things to come. So again, thank you all for your attention and for inviting me here. There's time allows, I'm happy to take questions.
Questions?
These government projects you're talking about,
Sorry?
these government projects you're talking about,
So partnerships between NASA and private industry. I think as I mentioned, some of those ones happening in the next 2 years are going up as part of NASA's commercial lunar payload services where private industry takes the rocket up. But NASA is funding scientists like me to plan for the project.
Laura?
If you succeed at some point in getting this constructed, will solar radiation provide any interference problems for you?
So that's one of the questions that Lucy Light is hoping to answer. So it will be very near the terminator. During the course of its mission, it'll spend some time in the day side, and it only has enough batteries to last about 1 Earth day of lunar night. But to tell us if we can do these observations during lunar day, or if we need to combine them to the 14 days of lunar night. There's also the question of whether it can last for 5 years with the harsh radiation environment. That's a big engineering challenge.
Right back, yeah.
I think you mentioned it earlier in your presentation, but what is the historical time period of dark ages?
So yeah, we don't know for sure because we haven't observed them, but some rough numbers. I go back to this timeline. This timeline is not quite as good as this one. About 400,000 years after the Big Bang is when the cosmic microwave background forms. We think the first stars are something like 100 million years after the Big Bang. So it's a small fraction of the 13.8, but it's a large chunk of cosmic time.
So there's this idea that electrons from the solar wind can go into lunar craters and create this region of like that's negatively charged. Would the lunar crater array have any interference from that?
It's completely possible. So studying that is one of the major goals of the two Lucy experiments, is whether there's the negatively charged region down near the South Pole, how that will interact with the radio antennas. But ultimately, is that the challenge is modeling these antennas to really high precision. And so if the lunar regolith has its own electromagnetic properties that change or interact with the electromagnetic properties of our antennas, if it breaks them, that's a deal breaker. If it changes them in a way that we can model, it's something we can handle.
Let's say an ideal environment, all this stuff is already built and we're getting all this great data. Is this going to give us a more detailed map of dark matter and gravitational concentrations, gravitational lensing and stuff for going all the way back to the background radiation?
So it certainly depends. I mean, statistically, we will get a measurement of that power spectrum like we had with the cosmic microwave background. The 5 square kilometer number is for a good measurement of the power spectrum. If you want to map, it's going to be even bigger than that, unfortunately. The statistics gives you the extra sensitivity. But 5 square kilometers sounds ambitious enough to me, but you never know. I think certainly from the ground, we're hoping something like the square kilometer array can provide that image, like that movie of the reionization process that I showed, that the SK could actually provide a movie.
Once again, thank you so much.